This is worksheet 4, wrap it up, which is, yeah, just more simple harmonic motion practice. The first question here is just asking, what is a requirement for something to be called a simple harmonic oscillator, and explain what this requirement means. So, really, a simple harmonic oscillator is just any object that is undergoing simple harmonic motion, that repeated back and forth motion, right? So we've seen like pendulums, right? This is going to swing back and forth because there's going to be a restoring force, right? We have Fg, Ft, there's going to be that Fg, X, that restoring force that is going to point back to equilibrium. There's springs, right, that are also going to, have that, or, point back to equilibrium. You could even have something, I don't know if this really counts, but I got a fan right here in my room. There's an oscillate button, it goes back and forth. So I'm sure there's going to be forces on that fan that are going to cause it to oscillate back and forth. Now it's going to do it at a constant velocity, but still, hopefully you get the idea. It's really this idea of restoring forces and simple harmonic motion. So for number 2, it's just some graphing. Horizontal spring has a block attached to it, and we're displacing it from an amount plus A, and then we're releasing it to let it oscillate back and forth, and sketch the graphs for 2 complete oscillations. We've done this a million times at this point. It really feels like it's just this kind of problem. But yeah, we know initially the position is at positive A, right? It's going to go to equilibrium, it's going to go to negative A, and then go back. Because of space, I'm only drawing one oscillation, right? It's going to go back, or it's going to go front and back, right? But of course, you should draw it's 2 oscillations like that, right? So there you go. I just drew it, because why not? Velocity, we're just graphing the slope. Slope right here is basically 0, starts at rest, boom. It becomes really negative, goes back to 0, and then goes to positive, goes back to 0, and then we cycle through that one more time, and you get your sine graph. And then we can have it come back right here, right? The slope is 0. And then we're doing acceleration. Same thing, we're just graphing slope. So right here, slope is negative, and it's 0. And then you can get your graph like so. And you should get, 2 cycles of, something like that. So yeah, there you go. Hopefully this isn't anything crazy. Now for the math stuff. The spring above requires a force of 8 newtons to stretch it 16 centimeters. What is the spring constant? So we just got to think about, the force exerted by the spring at 8, it's negative kx, so it's 8 newtons for, I'm saying there's a negative here, but it's absolute values, right? This is just the size of the force. So the size of the displacement is 0.16 meters. You should get a K of 50. 50 newtons per meter. There you go. Now for C, what is the period of oscillation? If the spring is pulled back only half that amplitude. They didn't give us any sort of period of oscillation. They don't give us K. They don't give us the mass. So obviously T is equal to 2 pi square root m over K. So I'm guessing it's just talking generally what's going to happen. And the period of oscillation is going to be the same, right? If it's only pulled back half the amplitude, it's still going to take the same time to, oscillate back and forth. If the block has a mass of 0.5 kg and it's pulled back a distance of 15 centimeters, what is the period of oscillation? We're just doing T equals 2 pi square root T spring equals 2 pi square root m over K. We know mass is 0.5 kg. We just solved for K is 50, and then you can just kind of solve from there. So I got 0.628 seconds. When you plug this all into your calculator, I got 0.628 seconds. How does the total mechanical energy of the system change when the amplitude is doubled? Justify your answer. So remember that all the energy initially is equal to the energy final. We're not seeing any loss of energy. So if our initial energy is U spring equals K, we know that, well, this is the total mechanical energy, right? It transforms, all the total mechanical energy transformed to U spring to K. So we just do 1/2 Kx squared is equal to U spring, which is also just equal to the total mechanical energy, right? Because that's where all the energy is stored initially. And then it's just proportional reasoning from there. If you double the amplitude, right, you square, you get 4 times. You get 4, so 4 times the energy. So hopefully that kind of made sense there. For the last problem here, you had to go to a video and you had to calculate the length of the lamp wire. So it was this like sort of performance. They had these lamp, thingamabobs. I don't know what you call them. They're just pendulums, really. They swung back and forth like so, right? And then they swung. What was the length? In order to find that, you would need really only one thing. And this is kind of interesting. You just need the time. This is all you need to measure. So you would literally have to pull out a stopwatch and then time it. I got a time of 5.63 seconds. Maybe you could get a more accurate result. I just timed one swing, but I got 5.63 seconds. We just do t is equal to 2 pi square root L over G. If they're solving for L, sometimes I like to just do t squared equals 4 pi squared over G times L. I like this one when I'm solving for L, but still, you just needed time, because G we know is 9.8 on Earth, where they were performing the Tony Awards. So, yeah, I think that's really cool. You can just, if you know the time of a pendulum, you can figure out the length, and that's a pretty powerful principle. So yeah, that's why physics is beautiful. Thank you for watching, and yeah, I'm gonna do the practice test now.